Hi everyone, today I'm talking to Randy Kuang regarding quantum encryption with quantum permutation pad in IBMQ systems. We're going to be very focused on a particular, let's say, encryption methodology that Randy has developed, and we're going to focus on how you can put that in place, partially in theory, but then also for some practical implications on IBM systems. I hope you enjoy that. I think in order for us to kick this discussion off, we can talk a little bit about your background. We were just touching upon that topic before starting the recording. So if we resume upon that track and you could paint a picture of what led you to publish the research on quantum encryption that we're going to be talking about today.
Okay, so in the past few years, most fundamental field might be quantum computing, and the most of experts is in the quantum computing, basically building up the computing power, and which come up to actually crack the classical encryption. So everything you have a good pro and con. Good, you can do powerful computing. Bad, you put the security in dangers.
Mm-hmm.
So it is actually I struggling with this field over a decade, starting probably around 2000 when I was working in Nortel. Then I feel okay, looks like information we can do quantum science for the security.
Mm-hmm.
You do the physical implementation for computing power. So you have a left and right, everything you have two sides. Building the power, break these things, then this side come to defense. So I say, what we can use quantum mechanics to do to defend this threat.
Uh-huh.
So this struck me over decades to figure out how to do that. So we figure out how we can take the advantage of quantum mechanics as a mathematics, as a science for security, not for the computing power. Computing power always relate to physical implementation, right?
Mm-hmm.
But the security power, you don't need. You don't need. So you basically you depend on the mathematics. So I'm seeing everybody talk about the uncertainty from QKD
Mm-hmm.
back to 1984.
Yeah.
What is fundamental behind that is the uncertainty principle, right?
Mm-hmm.
Everybody describe the photon can be here, this state, that state, uncertain. What does that mean in mathematics, in quantum mechanics? Means your encryption operation not commutable.
Mm-hmm.
Uncertainty is x, y minus y, x is not equal to 0. Like you usually use everybody understanding example. Wash your clothes and dry your clothes. These two operations cannot swap the position. You
Right.
cannot dry first and then wash it. Results is
Uh-huh.
different. So mathematics means you have two operations. They cannot swap the position to operate the order to operate. So if you can find that, boom, you have a good encryption mechanism.
Why is that?
We knew, Shannon, okay, Shannon proved a perfect secrecy for
Mm-hmm.
OTP one-time pad. That is the best scenario you can use to encrypt the data, but unfortunately, you can only use for one time. If you use second time, you will lose security.
Mm-hmm.
So this is already proved in the World War II, You can break this, Germans communication, So the problem is the operation used in one-time pad XOR is commutable. So you can use cipher or XOR cipher. They can cancel your key. So we needed an encryption mechanism. You cannot change the order. I think what it is. So I thinking, reading this Shino's paper for 10 years. Then I said, oh, we found it. Permutation. In quantum computing, permutation operator or permutation gates is there. Everybody understand. But this operation does not contribute any computation power. They just change shuffle the state. But it can be used for security power. So I figure out that then we just need to re-express classical information, use quantum way, use a kit, the direct kit. So one simple example, 8-bit information, classical information, 8-bit. How many possible classical space you have? 256, right? 256, 56. That's it. But if you express or lose this information using quantum mechanical way, then this will be create another space we call quantum permutation space. You permute this 256 states, you will form 256 factorial, this many operation. So this operation we call permutation operator or permutation gates. So in that way, you have so many 256 factorials equal to 10 power 507 possible way. Unbelievable, So this is very much like Einstein found, once your speed switch to light speed, your mass become infinity. The entropy is same thing. Once you describe entropy in classical way, it's very limited. But once you describe it in the quantum mechanical way or quantum computing way, there's a factorial, 2 power n factorial. This is endless, and this is there. It's not means we found it today. No, it's always there. The first guy found this is Galois. Is a young man. Galois found this. He created this permutation group. So then we take this to formulate a mechanism we call quantum permutation pad. Use this pad to replace OTP one-time pad. So now quantum permutation pad behave like a permutation. Simply permutation, each permutation is not commutable. That means you use the first permutation to get a combination. The second permutation get a combination. You cannot swap it. This is bilateral, So this is perfect for encryption mechanism. So we formed this QPP, quantum permutation panel. We officially formed this term back to 2020. So we established this system we call key space. We can use this exactly like a QKD to shipping random number over internet digitally.
Okay, so let me interrupt there for a second because there's a lot of interesting tangents here that we could linger on for some more moments. You mentioned now these permutation operators. First of all, I would like to get a bit more intuition for what those means. What do we actually mean when we say that we have this space that's generated by these permutation operators that take on such higher orders of magnitude in terms of entropy than the classical counterpart? If we start there, I would also have follow-up questions on, let's say, why this is relevant for encryption. But let's start there, I think.
Yeah, the permutation operator is just a permutation gates, like a quantum computing gates. They operate on a quantum states, a system quantum state. They permute their state into another combination uniquely. You can think about it like that. So this permutation the operation is the they can operate on the classical information states. They can also operate on the quantum system because they're scientifically they're same. So
Yes.
this paper is basically we implement this in the quantum computer to see whether it works.
So let me play the stupid role for a second here. I imagine that you would. So given that you have a qubit, let's say that you're manipulating with this quantum operation or this gate, you could, technically speaking, permute that state, as far as I'm aware, into any configuration that you would like. Given that this is a continuum, you have an infinite number of permutations that you potentially could apply. Now, I assume there's some restriction that applies here as well, which means that we have a fixed number of possible permutations. Could you shed some light on what those restrictions are that limit us to only, but nevertheless having a fixed number of permutations that are possible? What is it that puts that constraint on the problem?
Okay. If you're using the two qubit system, okay, as a simple example, two qubit system, you have 2 power 4, 2 equal 4 states. Okay, you have 4 states: 0, 1, 1, 0, 1, 1, 1, 0, 0. There's 4 states. So permutation, there's 4 states regularly you put in the order classical. People always assume like 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. You put this in this order. Everybody assume like that. However, you can use the permutation operator, basically behave like a gate, quantum gate, to operate this normal order, then produce a new order. They might become 0, 1, 1, 1, 1, 0, 0, 0. This is one possible. So then how many possible cases you can produce? Total is 4 factorial, 24 cases. Each case associated with a gate called permutation gate. In this case, 2 bits permutation gates.
Okay.
That is what we demonstrate in this paper.
Okay. That's very good. So then you have a superposition between these 4 states that we were talking about in this case, and that leads to 4 factorial number of states in total. What about the constants ahead of these? So you're able to create a superimposed state of these 4 states, and you have a constant for each one that you could manipulate. What are the restraints on that? So we're saying now that we have 4 factorial number of states, but I would say, in contrary to that, you have an infinite number of states because you can adjust how big the constants are associated with each, like how big the amplitude is. That's probably coming at it from a naive perspective, but why is that not possible?
Okay, so permutation operators always operate on their computational base. So your superposition states is a combination of all the possible computational base, right? So the difference is their coefficients, represent their probability to find the system in United States. So the permutation operator is operate on the superposition states, behave like operate on each individual computational base. Then after that, they form a new superposition state. So we have actually the sister paper with this one. We published this year called use a quantum permutation, but for the superposition state. It works in that same way. That is beautiful,
We can link that in the description of the video as well.
Yeah.
Okay, very good. But then let's transition to what this has to do with, or why it's useful rather, for the sake of encryption. Would you mind shedding some light on? We have this computational basis now that includes a lot of possible states, or I don't know whether states is the right word for it even. But given this large set of combinations, why is that relevant and useful for the sake of encryption?
Okay, thanks very much. Actually, you probably notice a lot of confusion in quantum communication or quantum encryption. Most people refer quantum encryption means use a quantum key through the QKD They encrypt the data. They call quantum encryption. Actually, that's not accurate. Quantum encryption should be use quantum operator encrypt this in the quantum state. Okay, so quantum permutation pad has this capability by side, dual behavior. They can use the front operate the quantum state inside the quantum computing system. Then, if you want to transmit out, you make the communication to another computer, which could be classical computer, which could be quantum computer. If the communication peer is a quantum computer, connect with a quantum channel, that means they can carry qubits. In that case, we use the QPP quantum permutation pad encrypt the state, sending out over this quantum channel to receiver. So that side can automatically decrypt back still in the quantum state. This quantum secure.
Right.
If your communication peer, like you talk to me, which connects so the classical channel, if they cannot carry quantum bits, then what you do, you still encrypt in quantum mode, then using the physical module to mirror it, sending out the cipher bits to another side. So another side use classical computer, they still can decrypt back into the plain text. So this is very much like, right now, probably between you and me, we have so many segment of connection, which might be Wi-Fi, which might be fiber. So this very, very much like, you can build the quantum computer system. You have a module, physical module to do this translation, So this will work directly. They'll bridge the communication between different computing systems.
Okay. What is the state of quantum channels right now? Are they in some way permissible? Like, is there research that's pushing this part of investigations forward, or what's the current state?
Actually, they are still in the initial phase. Last year, when I visited Germany, we talked to IBM, and they said they are in implementation for quantum channel. So right now, still not available. Once that's available, that means they have a quantum channel connected network. This can directly work inside quantum module.
Okay. And so currently then, if I understand that correctly, there are no quantum channels operational at the moment altogether. Like regardless of the distance we're talking about, they're simply not feasible at the moment.
They might have some research in the lab to demonstrate this, but not commercially available. Basically, like people talk about the quantum channel like a QPD one. QPD is not for communication anyway.
Okay. I'm trying to pull up part of the paper or figure from the paper here on the screen, and I figured we could have a look at that now. This has to do with the encryption scheme then that you've developed. Specifically, this is the encoding part of it. Would you mind giving a high-level explanation for what this figure we're looking at now represents?
Okay, so here we just propose to implement this in the universal quantum computing system. So in order to make this commutable with the classical system or another quantum system, so we have the three major components called pre-randomization to make the quantum states to be randomized. Then we have this called dispatching, so which means each qubit after randomized, they distribute to different quantum gates, different permutation gates. Then after that, the output will be cipher quantum states. So cipher quantum states right now in this paper or in today's quantum computing system, you can mirror it. Mirrors, they will collapse into classical bits, the bottom, the
Uh-huh.
classical bits. So this classical
Mhm.
bits should corresponding to the cipher text.
Okay.
We proved that, actually we demonstrated that working exact same thing as a classical system.
Okay. Okay. So maybe let's focus then to put this into context on the three different sections of this figure here on the left. You have the classical qubits or the classical bits, sorry, on the bottom here, and these were the ones you mentioned. I presume then that after the measurement here, where you actually encode the information in the classical bits, those would be sent over a classical communication channel and
Yeah,
then decoded on the other side.
that's right.
Would you mind explaining the purpose of these two other ones? Why do we have two sets of qubits here, and what's the difference?
Oh, thanks very much. You know, the first, the top, this is control bits, that's
Hmm.
the key. Your key, how you encrypt this quantum system, right? You have
Uh-huh.
your encryption key bits, the bottom is
Yes.
your data bits,
Uh-huh.
the data. This data right now in our implementation is the classical data. So we're loading
Uh-huh.
classical data. The top one we have the key. So use the key to control which bits, which qubits is being operated by which quantum gates. This
Uh-huh.
is that's like that.
Okay. And how come this is represented by means of qubits and not regular bits? Is there a need for them for this key to specifically be quantum, let's say, also, or is that more of a let's say means of illustration that you can do it also with qubits, but that you don't necessarily have to?
So you know to encrypt the qubits, you need the key bits, right? So that is input from the user or from the system.
Uh-huh.
So you have to use that to represent this. So that's basically the top part is designed for that.
Okay.
It
Okay.
simply your key, okay?
Right.
Or the key can be randomized through the internal algorithm too. But
Uh-huh.
that's associated with the encryption key.
Uh-huh.
So always, for data encryption, even in classical, you have a classical data, then you have the key, then you have this encryption module. This is very similar. You have the
Uh-huh.
data coming in, you have the key from top, then you have an encryption module, output is cipher.
Uh-huh.
Very much
Okay.
like this classical one.
Okay. So with this one, then it would be pre-shared between the sender and the recipient, and it
Yeah.
would contain the information necessary to do the proper encoding, but then also the proper decoding of this message.
Yes.
How
Yeah.
would you go about sharing this as of now? Is there a
Okay.
good way to do that, or?
This this different area.
Mhm.
So first we consider this, for some high security system,
Yeah.
they request pre-shared secret for trust.
Uh-huh.
So once you have that part, they don't have problem. They can directly start to work. Less than the high security requirement, like today's TLS,
Uh-huh.
and the user-based encryption. You can use a public key scheme to establish shared key on both ends. Then you can transfer for to data encryption. Here you
Mhm.
can use that pre-shared established shared key to drive this encryption.
Uh-huh. Okay. So if we then look at how the information flow for the actual plain text qubits that we will then turn into the ciphertext ones, we have first of all a quantum initialization operation here, and
Yeah.
correct me if I'm wrong, but this is just to initialize the qubits in the correct state and
Mm,
to encode the necessary information.
yeah.
I think the one part that's more interesting then is the quantum randomization procedure. Would you mind describing a little bit why this exists and what the negative consequences would have been if that wasn't part of the system?
Okay. This design is trying to make it work with classical system.
Uh-huh.
So in classical system, um, plain text is always not truly random, right? It's very structure oriented.
Yeah.
So quantum permutation pad is a perfect, is a zero perfect type of encryption, the bijective mapping. So if your input has structure, has pattern, output, the ciphertext also have pattern, So this is basically linked information. So in order to overcome that, you always have a pre-randomization, later quantum encryption just at the last step, Very much like AES, what AES does.
Okay. By the looks of this, I would say it looks like we're transferring the problem of randomizing the qubits here to the key qubits. Given that the key qubits here, depending on, I guess, their values, we would scramble this in one way or another.
Yeah.
How would you initialize this secret key qubit such that you would actually get a reliable scrambling here? Is there anything in particular, or a good randomization?
So in our proposal, we have this randomization scheme, and to take this sheer secret, then use a good randomization scheme to produce this pseudo random number, which is very good if you can use this random list testing tool that pass everything. So basically, you can use a list standardized pseudo random number generator. So take the secret key, then use the module to produce a good random list. Let's use that good random to randomize the plain qubits. After that, the plain qubits will show very much random uniform distribution for the states, 0, 1, 0, 1. So then you use a quantum permutation path to encrypt it. This is bijective, so you don't have this pattern in the cipher qubits.
Okay, understood. So maybe we can talk about the quantum dispatching procedure next then.
Yeah.
We again have a reference here to the secret key qubits, and we use some gates to produce a form of dispatching. Would you mind describing what the purpose of that is and how it works?
Yeah, cryptography. There are two terms. One is called diffusion, one is called confusion. So good crypto scheme must will consider this. So in this case, you say we have a permutation path, permutation gates, many. So for each plain qubits after the randomization, which permutation gates you want to send in should be uniformly distributed. You can send in the randomized qubits to each individual permutation gates equally likely. So in that way, nobody can guess what you guess the original order. So this is used to enhance the diffusion capability. So pre-randomization actually give you confusion capability, the diffusion capability. After that, permutation map to another domain. So then you gain a perfect randomized ciphertext.
Okay. So quite simply then, the line that I'm drawing here with my mouse now, at this point is where we've randomized the input, but nevertheless, this is an unencoded randomized input of information. And then we want to apply this permutation that we discussed in the beginning. And given that we have this, 2 to the power n factorial, I believe, number of possible states, we want to assign those equally likely, or with the permutation operators to each one. Okay, and so this one just positions, if you will, the permutation pad to. Okay, very good.
That's right.
How do we do that in practice? So what are these gates that we apply between the secret key qubits and the plaintext qubits to perform this switch?
So each after initialization, you already pick a path of these gates, right? Created. So this permutation matrix is then compiled by the IBM compiler to they form this permutation gates. Then you based on the random pseudo random number. For example, we choose just like if we choose 64 gates, if your random number PRNG number equal to 35, you distribute this qubits to 35th gates to do the quantum encryption. So that after encrypt, they fill back to the in order to form this cipher qubits. So everything is controlled by the the shared key.
Mm-hmm. Very good. And then the permutation operations here are really the same kind of gates, irrespective of which time this applies. It has, as you also indicated in the figure, no reference to the secret key qubits.
That's right.
When we then perform measurements on the plain text qubits, or rather the cipher text qubits at this point, to encode those into the classical bits in the regular communication channel, how does that work? I mean, you can measure a qubit, but then you're collapsing the state in some way. And my understanding is you would like to preserve the state given the fact that we're making use of the entropy associated with this larger space of superpositions. Would you mind shedding some more light on that?
That's right. Actually, before we do this, we don't know it. We don't know it, So my colleague Maria first did this experiment. Then they tell me, "Hey, Randy, I get different value, different time, I said, okay, that is what quantum computing, the probabilistic,
Right.
So I say, do this, measure 1,000 time. Okay, measure 1,000 time. Let's see the results. So that you can see the probability distribution. Once you shoot in 1,000 time, they come out the results. The most probability state is the classical one. So this perfect match, for every encryption, if you shoot in 1,000 times, they come out. One means the probability is the most probability result is the classical one. So that's actually quantum to classical. It's perfect match like that. So it's not for each encryption. Each encryption, this is random. But if you are shooting for 1,000 times for each case, you gain a distribution. Then they demonstrate the classical way.
And is that what you would do? So for any given transmission, let's say, of a message here, you would actually transmit the message a large number of times, and then the receiver would encode a large number of messages and use some probabilistic approach for then deciphering what the qubit states were.
That's right. That's right.
Okay.
If you do measure, because quantum system, once you measure, you change the system, the collapse by probability, right? If you don't measure, then they still stay there. Don't touch it. Then the next operation they will go back. But once you measure, you take the quantum to classical to a digital. You did shooting many times. If you keep quantum, don't have problem.
Right. Okay, very interesting. So with that, I think it makes perfect sense to move over to the decryption aspect of this, because we've seen now then how to conceptually at least encode one of these messages and send it across the channel. I'm sharing now the diagram for how to decode the received signals, and maybe you can give a quick introduction to this one as well, and then we'll get into some more details.
Yeah, so you say we are almost mirror the encryption side. Okay. So we have a randomization, we have this dispatching, we have this decryption. So because permutation is reversible operation, so this in the receiving side, the permutation pattern must be transposed or reverse the gates.
Right.
Okay. So then the randomization will be after, because randomization is behave like classical. Okay. So there will be last step, you de-randomization the back to original. So here is a first you do the distribution, then decrypt. After that, de-randomization. You bring back the plain text.
Uh-huh.
To verify that, you same way you do this measure it. But if you measure one time, random, you don't know. If you measure some time, they exactly show you what's the plain text.
Okay. I get the rationale of this, and it makes perfect sense that the first thing we would need to do is dispatch, because naturally we need to dispatch before we apply the permutation pad, because, well, the secret key qubits contain some information, right, about where we want to apply a given inverse permutation. So we need to have this one before this one. That's perfectly clear. And also we need to de-randomize, I guess, after we've done the other transformation.
So here the distribution must be first, because which qubits included by which permutation gate must be decreased by corresponding reverse permutation gate, right? So the order must be the same, otherwise it will be screwed, you know. So after then, you do this de-randomization, they will bring back. Yeah,
that makes perfect sense. What strikes me as surprising is that we have the measurement operations here, or operators, somehow after this entire pipeline. And I'm not able to. So, given what we said before, we said we would transmit this a number of times, and we would transmit the information through a classical communication channel using the classical bits. How do we go from receiving the actual signal in a classical sense to somehow transferring this back into a set of qubits that can be operated on in the following way?
So, first, I want to clarify, if you have a quantum channel from the sender to receiver, for example, you just put it in on the disk, then transmission side, you don't need to do this measure into the ciphertext, into the bits,
Right.
So then it's the receiving side. You don't need a reinitiate this cipher bits into the cipher states. So then you can send in the plain text, encrypt, transmit over quantum channel, then decrypt. Then you gain the plain text. You should get the plain text like what you send in, For example, you send the hello world. Receiving side, after you measure. Of course, if you measure one time, just random. You measure once, you shoot in one sound time, they give you hello world. Takes the most probability measurement.
Okay. But nevertheless, so that aspect is clear, or on a high conceptual level, that's clear. We send these through, and if we had better quantum communication channels, we wouldn't need these classical bits to begin with. We would just encode some message, send the ciphertext qubits across, decode them directly, just as you said. Yeah. Given now that we don't have this set up currently, we somehow encode the message, we send the classical bits through a classical communication channel. As you said, we generate in some way, and this is what I want to get to in more detail now, in some way we get back the ciphertext qubits from this signal, and then we can decode those. Yep. From my perspective, it's perfectly clear how we go through this decoding procedure after we receive the ciphertext qubits. What I don't understand right now is how we go from the classical ciphertext bits and transform those back into a set of ciphertext qubits.
Oh, okay. So this in the transmission side, you already measure, you gain the ciphertext string, right? So then you want to use this quantum decryption. So you, based on the take this classical ciphertext, then reinitiate this, convert this to the quantum qubits.
How do you do that?
The system, for different system, quantum system are different, okay? IBM system, you can use their initialization to assign each qubits, create a qubits with associated with the value for the states, for the qubit state. So for each qubits you create, you can set their value, their state to 1 or 0. So that
Uh-huh.
you print, you gain this corresponding cipher qubits for
Uh-huh.
this as an input.
Uh-huh. Okay. So let me reiterate it again then, just to make sure I understand. You send across this a number of times, you receive it on the receiving end, you have a set of, let's say, 1,000 batches that you've sent across, and you've recorded these. You take those 1,000 batches and you create a probability distribution associated with the values of those, and from that you can then reconstruct what the qubit should have been. And then you do that in the system, and then you can feed it through the decryption scheme.
Yeah, in general, your description is correct.
Okay.
But in reality, when you do it, you for each initialization, you can request the IBM quantum computer say how many times you want to shoot for this initialization and decryption. You
Uh-huh.
tell them, I want to shooting for 1,000 for this configuration, for this
Yeah.
decryption. So that they
Uh-huh.
direct give you what the plaintext is.
Uh-huh.
You use the most probability results.
Uh-huh. Okay, very interesting. Let's maybe focus on how well this works compared to some classical encryption schemes, if there is a natural comparison to do like that. And then, as a final question, I would want to be interested in like next steps for this research. But maybe if we talk briefly about results first and what you found after performing this kind of encryption.
So that's a very interesting question, Nicholas. Well, today research is trying to implement encryption inside the native quantum computer. Like AES, it's very difficult. Okay, it's very difficult to implement. They need a lot, billions of these circuits.
Uh-huh.
So with this QPP, it's very minimal. Basically, it can work with any universal quantum computer.
Uh-huh.
So use a very limited quantum resource, we can do that. We can do that. But today, because this quantum system still very limited capability, so it's need
Yeah.
10 years, it's 10 years. But from understanding, it's perfect at doing this. Once we have the mature quantum system, with this embedded into the system, you are
Uh-huh.
similar like what we have now, like what where our communication is.
Mm-hmm.
So what I'm saying, if we really want to do quantum encryption inside a quantum computer in years or what we can see the time, most likely this QPP is achievable one.
Okay. In terms of next steps for the research that you would like to do as a consequence of this investigation that you now conducted, would you mind shedding some light on that? Where do you see the research going? Yeah, if you look forward.
Okay, so if you look at our fundamental paper published in the Springer Quantum Information Processing back to 2022, I think, uh, in our vision, we see in the future quantum computer very much like today's classic computer, modularized. Okay, they
Uh-huh.
have different physical module. They might have a module called quantum module. So in that way, for user, you even don't know. You don't touch that. Like today, you don't touch your computers with the optical connection.
Mm-hmm.
The module physically will do. All of this, what we talk, will be in that physical module or data module that do this naturally. So you will
Uh-huh.
never know, realize that. So based on that, we say this research and actually pave or give a direction in the future quantum system. Once it mature, you have the capability, to do quantum secure communication between systems, maybe mixed system, hybrid system,
Mm-hmm.
using this way. So they are quantum encrypted, communication,
Uh-huh.
which is much easier. And you can see, you show me this table. This is the ciphertext actually measured. Okay, we measure the encrypted qubits into cipher. You can see the randomness of encrypt.
Uh-huh.
very good
Mhm.
randomness, even in this very limited 5-qubit system.
Uh-huh. So is there anything in this investigation here, these numbers of randomness, that you feel would
Okay,
require further exploration or further improvement, or what are sort of the next steps in terms of trying to make this even better?
so of course we can this is just demonstration purpose, You can
Uh-huh.
say first column is our ciphertext million, ciphertext million. And the last term, last column is the plaintext. You can say plaintext for 8 bits, they are 7.3 bits. They're not random, it's very structured.
Uh-huh.
And also the most important is they call chi-square. The
Right.
chi-square should be around 256 ideally. But
Hmm.
this is a huge, means totally biased data. But in our, the 2-qubit system, we gain this, chi-squares 277 with the
Uh-huh.
probability, the 0.1156. This being treated as a random, it's a random case.
Hmm.
And you can see they even molecular pi, we will produce 3.1 or 128, very close to 3.1414, and the plain text is different, slightly different,
Uh-huh.
So, so this you can see, even you with this very limited demonstration toy example, they already demonstrate you can turn a plain text into good random cipher qubits
Uh-huh.
to
Okay.
to
And
offer security.
right. And to make this, let's say, operationally available on a larger scale, what are the current limitations that you see? So I guess communication channels are one, but it seems that based on the results we've observed, you don't necessarily need those to be able to implement this
Yeah,
in practice. I would suppose that stability issues and things like that are larger concerns, but would you mind shedding some light on those aspects?
yeah. Actually, for what we need the security today, probably we can implement a 4 qubits QPP. Each gets equivalent to 45 bits entropy.
Uh-huh.
4 bits QPP can be implemented in today's system, like IBM Osprey.
Uh-huh.
However, they lead their fidelity be higher. So now the fidelity is too low, just 99%. So they cause a lot error after certain operation. We have tried, for 4 qubits QPP, after you compile from this physical, each
Uh-huh.
operation give you 1% or 0.1% difference after 100. The error is big. Error is
Right.
big, you cannot use it. So this is why
Yes.
we limited to, we use this 2 qubits. 2 qubits, just the depth is about 15. It's very
Uh-huh.
good for the demonstration purpose.
Uh-huh. Okay, wonderful. So I think with that, unless you have any concluding remarks, Randy, I think we can actually bring the interview to a close.
So I think Nicholas, first I appreciate you gave me this chance to explain how this quantum permutation pad work as a mechanism to encrypt the data, which can be done for classical system and also possible for future quantum system. And in fact, they can bridge classical to quantum in the future.
Uh-huh.
Okay, I think this is a very promising one.
Hmm.
And for today's security, we can implement it classically and achieve this quantum encrypted random number sending or distributed over internet to
Uh-huh.
solve the problem for the quantum threat. So that's actually is a commercial offer from Quantropi.
Great. Then with that, thank you very much, Randy, for taking the time to join.
Thanks, Nicholas.